After properly completing the dilutions of copper sulfate pentahydrate, you'll need to transfer a sufficient amount of each dilution into cuvette in preparation for the use of the spectrophotometer. Gently wipe the two sides of the cuvette where the light will pass through. The first cuvette you'll use in the spectrophotometer will contain just water. This allows you to zero out the machine before scanning your solution. Failing to zero out the spectrophotometer with a blank will cause all your absorbance values to be inaccurate due to calibration errors. Begin by scanning your stock solutions across all wavelengths. The spectrophotometer will produce a graph showing the absorbance of your solution at various wavelengths. Your task is to determine the wavelength at which the absorbance reaches its highest peak, known as the lambda max. Here on this graph, we can see that the max is around 600 to 615. You will use this wavelength to measure the absorbance of the stock solution along with each dilution. To do this, you will need to change the wavelength setting on the spectrophotometer. Our max was around 615 nanometers. Once you've configured the spectrophotometer, you're ready to insert your stock solution to measure absorbance. After clicking read, the spectrophotometer will display the absorbance value on the computer screen. Make sure you record this value in your notebook. You'll need to perform each of these steps with every dilution, being sure to wipe the sides of the cuvette every time, and then record the results diligently. Once you've recorded the absorbance of all your dilutions, use the spectrophotometer to determine the absorbance of your unknown. The spectrophotometer will record all the absorbance values in the order in which you read them. The recorded absorbance values and calculated concentrations will allow you to determine the relationship between the absorbance and concentration and, in turn, calculate the concentration of the unknown solution. The absorbance of the solution can be determined through the relationship between concentration and molar absorptivity used in the Beer-Lambert law. When analyzing an unknown chemical compound, it's essential to scan across all wavelengths. This approach allows us to detect the specific absorbance peaks of the compound. Each chemical substance has a unique lambda max representing the wavelength at which it absorbs light most effectively. By scanning across all wavelengths, we can identify the lambda max in the compound in question. Secondly, in chemical reactions, the lambda max of a compound can change as the reaction progresses. To monitor and understand these changes, it's crucial to scan across all wavelengths. By doing so, we can track the variations in absorbance throughout the reaction, enabling real-time monitoring of the reaction's progress. This is our data and calculations in correspondence to the volumes, 1 being our stock solution and 2, 3, and 4 being the following dilutions.